Welcome back to Chem Talks, guys. This is Mr. J. Today we are going to start talking about the gas laws. Previously we have talked about the properties of gases, but now we're going to move on and talk about some of the laws that govern gases, and we can use these laws to predict behavior of gases when conditions change. Let's start by looking at an example of a balloon. So let's say we take a balloon, as in this case, we blow it up, and we're going to put it in some liquid nitrogen. You guys all know that liquid nitrogen is really cold. When we put it into the liquid nitrogen, look what happens. It shrinks up. Well, knowing what we know about the properties of gases, and that we've already talked about, think what's happening. Remember, pressure is caused by the particles, in this case the gas particles, pushing against its container, which is the edge of the balloon. Well, what controls how much they're pushing against it? That is going to be the temperature, right? And we know liquid nitrogen is really cold, so when we put it into liquid nitrogen, we're going to slow those particles down, and when we slow it down, we reduce our pressure and our balloon ends up shrinking. Well, this and other observations like this are really important. From these, what we can do is deduce what we call the various gas laws. And that's what our vodcast today is going to be on. So the gas laws are simply the mathematical relationships among properties of gases. These properties that we've already talked about, things like pressure and volume and temperature and moles that we talked about earlier this year. Okay? By looking at these observations, we can figure out these various relationships that exist among these properties. Okay, now remember, we've already talked about this, but I want to remind you that for all gas laws calculations, we need to make sure we're using the absolute temperature, or the Kelvin scale. We talked about how when we do these gas laws, if we have negative values, the numbers start getting messed up. So that's why we use the Kelvin scale, because Kelvin has no negative, right? Absolute 0 is the lowest temperature we can get in that, so there are no negative numbers. So when we talk about gas laws, okay, we need to talk about them at STP, standard temperature and pressure. And as we already mentioned, standard temperature is 273 degrees Kelvin, 273 Kelvin, there's no degree sign, which if we were to translate it is going to be 0 Celsius, right? We just subtract 273 from it. And then our standard pressure is 1 atmosphere, or 101.325 kilopascals. The reason we need to talk about standard temperature and pressure is because when we compare gases, we need to be able to control some of the factors, so we don't have more than one variable changing at a time. So let's talk about some of the variables that we're talking about. Volume we've already talked about throughout the year. It's just a three-dimensional space that matter occupies. So how much area, how much room does something take up? We've also talked about temperature. Remember, temperature is just a form of energies, and temperature is a way of measuring. It's the property of matter which reflects the quantity of kinetic energy. Remember, kinetic energy is the energy of movement. Okay? So how quickly are those particles moving? We've already talked about as we increase the temperature, we're increasing the movement of particles because we're giving them more energy, and vice versa if we decrease the temperature. Pressure, this was new for this unit. Pressure is just the force exerted by the particles on the container. So in that first picture we had, the pressure is created by the particles, the gas particles, our breath, for example, if we use that, or helium, if we have a helium balloon, pushing on that outer container. And finally, one that we've talked about a lot this semester already is the mole. Remember, the mole is just a counting unit. Okay, it's a way of counting atoms or molecules or particles, and we said that 1 mole contains 6.02 times 10 to the 23rd particles, where those particles be molecules or atoms or anything like that. So gas laws these are simply mathematical relationships, okay, that compare the different properties such as volume or temperature or the quantity of a gas. And there are numerous gas laws. We're going to talk about 4 of them today, and then in the future podcast we'll talk about 2 more. Okay? So the 4 that we're going to talk about are Boyles law, Charles law, Gay-Lussacks law, and then finally Avogadro's law, which we've already talked about earlier in the semester when we talked about moles. So let's go ahead and look at these. Now for each of these laws there is an equation that you can manipulate to figure out how the properties are going to change in response to some other change. So let's look at Boyle's law to begin with. Boyle's law gives us a pressure and volume relationship. So we're looking at comparing pressure and volume. Okay, what we see, if we keep the temperature constant, okay, that's going to be constant, there's an inversely proportional relationship to each other. Now think what inversely means. Inverse means that as one increases, the other is going to decrease. So if our pressure increases, the volume then is going to go ahead and decrease. Okay? And we can represent this as P1 V1 is equal to P2 V2. Similar equation to when we did dilution. Okay? But in this case, P is our pressure, V is our volume. Okay? So these calculations typically will give you 3 out of the 4 and ask you to find the 4th one. So the key is figuring out who belongs together. Which one's P1, which one's V1, who's P2 and V2. So let's take a look at an example problem on this. If we have 75 milliliters of gas that's collected at 680 millimeters of mercury, what's the volume at STP? Remember, millimeter of mercury is just another way to express atmosphere. And so we know that 680 millimeters of mercury goes along with the 75 milliliters, and it wants to know the volume. Okay, so we know volume 1 here. We know pressure 1. It wants to know volume 2. But what's our second pressure? We're only given 2 variables. Well, it tells us that at STP. Okay, and so we can assume then that STP, remember, is 1 atmosphere. Well, we'll have to do a little conversion on there. So let's look at our equation there. Okay. So we know P1, V1, we know P2 from STP, but we're trying to find our second volume. Okay, so if we rearrange to find their volume, we get this equation. That should be pretty simple rearranging for you now. If you have any problems with that, make sure you stop in and see me. Now, if you remember from previous discussions, we said that 1 atmosphere is equal to 760 millimeters of mercury. So at STP, okay, our P2, our second pressure, then is 760 millimeters of mercury. So if we plug the numbers out from above in, we end up with this. 680 millimeters of mercury times 75 milliliters divided by 760. When we do the math, it comes out to 67.11 milliliters. So basically just plug and chug once you figure out what everything is. Let's go ahead and try another one. Okay, what I want you to do in this one is, once I give you the problem here, I want you to pause the vodcast and do the problem on your own. Now, don't cheat. I know you can just keep playing and get the answer, but I want you to make sure that you're understanding it. So let's look at this first one. So 55 milliliters of gas is collected at STP. The pressure has changed so that the new volume is 250 milliliters. What is the new pressure in atmosphere? So go ahead and please pause the video. Try this in your notes there, and then we'll go from there. So here's our equation. Once again, P1 V1 equal P2 V2. We're solving for P2. So let's rearrange that. We get P2 there. Now it's just a matter of plugging and chugging. We got 55 milliliters is at STP. Okay, well, STP is going to be 1 atmosphere, and since or 101 point something kilopascals, but since we want in an atmosphere, so we're just going to use 1 atmosphere for that. Okay, so we plug and chug there and end up with 0.22 atmospheres. Hopefully you got this. Let's just do one more here real quick. Okay, flask containing 155 milliliters of H2 gas was collected at a pressure of 22.5 kilopascals. What pressure was required for the volume of the new gas to be 90 milliliters? Answer, once again, in atmosphere. So they give us originally in kilopascals. We're going to have to end up in the end convert it to atmosphere. So go ahead and pause this. Do it on your own, and then come back once you get the answer. Okay, so P1 V1 equals P2 V2. Again, we're solving for pressure again, so we rearrange. Okay, now I could either convert before or after kilopascals. I'm going to do the math first, okay, to find P2, and then I'll convert it into atmospheres. So if I take 150 milliliters, that's our V1. Here's our P1. Okay, and over here 90 milliliters is our V2. Plug those in, and we end up with 38.75 kilopascals. Okay, so now we have to convert. So 38.75 kilopascals is equal to 1 atmosphere is equal to 101.325 kilopascals. We do the math, it comes out to 0.325 atmospheres. Charles' law. And Charles' law looks at temperature and volume relationship. And unlike Boyles' law, what we see is that temperature and volume have a direct relationship, or they're directly proportional to one another. Okay, when we're holding our pressure constant. And so what that means is as one increases, the other one increases. So if we increase our volume, the temperatures increase. Or just the opposite. If we decrease temperature, we're going to decrease the volume. So we have a slightly different looking equation. In this we have our volumes over our temperatures. We set them equal to each other. And it becomes, once again, just like Boyles, a little plug and chug. They give us 3 out of the 4 quantities there, and then we have to find for the 4. So let's look at an example problem here. A 14.9 milliliters of gas is measured at 25 degrees Celsius. If the pressure remains unchanged, what will be the volume in milliliters of gas at 40 degrees Celsius? Okay, so first thing we should notice is temperatures in Celsius, right? We want temperatures in Kelvin, so we'll have to deal with that. And so let's look at our equation here. Now let's put our numbers in. Volume 1 is 14.9, temperature 1, 25 degrees Celsius, add 273 to that, okay? And we want to find this second volume here, and our temperature 2 is 40 degrees Celsius, add 273. So when we solve it, or plug and chug it, looks something like this. So how do we get V2 by itself? Well, we simply take 313 and multiply it by the other side. So it looks something like this. Notice that we did change our temperatures both into Kelvin, and we do our math, it comes up to 15.65. Really important, do not do your math in Celsius. We have to do it in Kelvin, so change that. Okay, let's try one on your own here. So if the gas in a 1 liter bottle at 25 degrees Celsius can be put into 1 quart, which is 0.946 liters bottle, at the same pressure if the temperature is reduced. So what is the temperature required? If we're going to reduce this temperature, what do we need to do? So go ahead and pause it, plug your numbers in, and then come back and hit play once you get it done. Alright, hopefully you're not cheating. If you are, pause it and redo the problem. Alright, so once again, there's our basic equation. We're going to plug our numbers in. Once again, we're given 25 degrees Celsius, so we got to change that. Okay, and this time though, we're solving for T2. So we put our numbers in here. Okay, to get T2 by itself is a little more difficult, right? We got to move it over to the other side. But now we got to get rid of 1 liter, so we're going to divide 946 by 1 liter and then also multiply by 298. So if you're having problems rearranging this, please come see me. It's basic algebra and we can work on it together. So we rearrange it. T2 is equal to this. Okay, put our numbers in here, and we end up with 281.91 Kelvin. Okay, but what's the problem asking for? It's asking for temperature in Celsius. So to that we have to subtract 273. We end up with a temperature of 8.91 degrees Celsius. Okay, so you got to make sure you're answering what the question is looking for. Not Kelvins, but it wants degrees Celsius. Okay, try one more on your own here. 60 milliliters of N2 gas at 22 degrees Celsius. What is the change in temperature in degrees Celsius that must occur to have the N2 gas occupy a volume of 70 milliliters? So it's not wanting the final temperature, it's wanting the difference between the final temperature and the initial temperature. So go ahead, pause the video, and see what you can come up with. Alright, let's see what we got. Now, we want to find T2, okay, but that's not the end of this. So we're going to solve for T2 just like we did in the previous question. When we do that, we get a final temperature of 341.17 Kelvin. But it doesn't want the final temperature, it wants how much we change. Well, we know we start at 22 degrees Celsius, so the final change, I'm going to have to convert this to Celsius. So I'm going to subtract 273 from it, and I end up with a final temperature of 71.17 degrees Celsius. So it wants to change, so I'm going to take 71.17 minus our initial temperature, and we get a change of 49 49.17 degrees Celsius. So watch out for these little trick questions. What do they ask for? They want the final temperature, or are they looking for a change in temperature? Alright, our next law is the Gay-Lussacks law. And this is the pressure-temperature relationship. And like the previous one in Charles' law, it is a directly proportional, meaning as one increases, the other one increases. Or as one decreases, the other decreases. So if we increase temperature, we're going to increase the pressure. So our equation looks similar to Charles' law, except we're dealing with pressure and temperature. So it's pressure over temperature. Once again, P1 is our initial pressure, T1 is our initial temperature, P2 is our initial pressure, T2 is our initial temperature. And once again, they'll give us 3 out of 4 of these, and we end up plugging and chugging. So let's try one together, then I'll have you do one on your own. So 10 liters of gas is found to exert 97 kilopascals at 25 degrees Celsius. What would be the required temperature in Celsius to change the pressure to standard pressure? So what's our standard pressure? Remember, it's 101.635, I believe, kilopascals. So we have our initial volume, okay, but remember, the volume is staying constant, okay? So how do we do that? Think of like a scuba tank, for example, right? Even though the volume inside it change, the overall volume is going to stay temperature. It's going to stay constant. So here's our equation. We're going to want T2. So we're going to solve for T2 just like we did in the previous example. Okay. So here we're going to rearrange, and when we rearrange, we find our temperatures. Our final temperature is 311.3 Kelvin. It wants to have it in Celsius, so once again subtract 273 from that, we end up with 38.3 degrees Celsius. So hopefully by now you're getting comfortable rearranging these equations and working through them. Try this one on your own, see what you come up with. So 5 liters of gas collected at 22 degrees Celsius and 745 millimeters of mercury. When the temperatures change to standard, what is the new pressure? Okay. So go ahead and pause and work this out, and then come back once you're done. So there's our equation again. Okay, in this case we want our P2. So we're going to put everything in, and then when we rearrange from P2, we end up with a pressure of 689.44 millimeters of mercury. So hopefully this is pretty easy for you. If you're struggling, let me know. Come in and see me. Okay, let's move on to our last one, and this is Avogadro's law. And we talked about Avogadro's law, earlier in the year when we talked about doing our mole conversions. Okay, so Avogadro's is the volume-mole relationship. Remember, Avogadro worked with gases, and what he found out was that equal volumes of gases at the same temperature and pressure are going to have equal number of particles in them. Okay? And so volume is directly proportional to the number of moles in a gas at the same temperature pressure. If you remember, what we found out when we did our mole conversion was that 1 mole was equal to 22.4 liters. So we can actually write an equation for this. Okay, in this case, V is volume, and then N here refers to the number of moles that we have. So let's do a quick problem with this. So if we have 2.45 moles of argon, it's occupied a volume of 89.0 liters. What volume will 2.10 moles of argon occupy under the same conditions and temperature? So we are decreasing our number of moles. So we're going to set up our equation here, okay, and just plug in our numbers. So volume 1 is 89. Our N1 is 2.5. Okay, we're searching for V2, but we know our N2 is 2.10 moles. So if we put our numbers in there and then solve for V2, we end up with 76.3 liters. So nothing too difficult. Alright guys, thanks for listening. We talked about the 4 laws: Boyles, Charles, Gay-Lussacks, and Avogadro's. If you're having any problem with doing the rearranging of these equations, please let me know. Okay, come in and get the help. Otherwise, we will review these in class and do some practice. Until next time, guys, take care.